Yeah, so good morning, good evening, good afternoon, everyone. Yeah, as I said, Hoshin, it's no introduction, but he's one of the leading forces of this reading group and the information theory group in the geosciences. And he is gonna talk about his presentation on machine learning interpretable representations on dynamical systems. So welcome, Hoshin, and yeah, it's always very good to have you.
Thanks, Leela. I think you guys are seeing the wrong display, right? Or are you? What do you guys?
I was seeing the slides.
You are seeing the slides?
Yeah, before we were seeing your slides.
This
now
one?
I'm seeing
Now
your
we are
email.
seeing your email. Yeah.
There.
Okay. Actually, I'm sharing the wrong. So I'm sharing the wrong wrong monitor. Let me try again. Desktop 2. Okay. Now what do you see?
Perfect. Yes, we see your slides.
The actual full screen?
Yeah, the presentation mode, full screen.
Okay. All right. I'm missing this one. Bring that over here. Okay. And I did try to set up my whiteboard in case we have any discussion. So hopefully that'll work. I haven't done using one. So thanks, Leela. This is meant to be kind of a conversation. I gave this talk just a few weeks ago in the math department, and we had a nice discussion. So it's not like I'm claiming I have all the answers to this issue, which has been of interest to people now that machine learning has become so important. It's just that I've been thinking about this from a particular perspective, which is, how do we actually do reasoning in hydrology? How do we use models for reasoning? And it sort of occurred to me that if you want to do reasoning, then there has to be some meaning or interpretation associated with those models to allow you to do that kind of reasoning. And I'm sort of more strongly of the opinion that that the main reason we actually build models is for reasoning. But that could be part of the conversation. So I called it learning interpretable representations of dynamical systems. And just start background so you guys know me: systems theory, hydrology, machine learning. And basically I look at it as this sort of process of going from data and theory to information to models, which we use for both understanding and prediction, and then ultimately to make decisions. So there's always a decision in this loop. Yeah. Interest in representational architectures and information theory. And information theory, we talk about Shannon information, which is about surprise. It's about probabilistic representation of the world. And the main thing we get from there's a lot of things we get from Shannon, including how to do optimal coding and so on. But from the point of view of model building, the whole thing about Shannon is you want to minimize the conditional surprise of your predictions, right? Given your prior knowledge, you want to make sure that the error in your prediction is as minimally surprising as possible. That's your goal. So ultimately, that's the metric, right? From an information theory point of view, that is the metric that we want to use, or a metric. Okay. Then we've got algorithmic information, and Kolmogorov came along and Solomonov and pointed out that in addition to minimizing conditional surprise, we also want to minimize conditional complexity. So for the same amount of surprise, if you've got two different explanations, one more complex than the other, then you want to choose the simpler explanation. Mm-hmm. And they give some arguments about why you would want to choose the simpler explanation, because more complex explanations are less likely to exist in the universe. And that's another conversation we can have. Why conditional complexity? Because whatever your description is always conditional on some dictionary, some language, some operating system, some set of rules about how you calculate complexity, and so on. So for the longest time, I was just thinking about this as Shannon information and algorithmic information. And then as machine learning came along and I started to think about this more, I realized that probably there's another aspect of information that we need to consider, and that's this thing I call representational information. I don't know if this is the right name for it. It's the name I use for it. It's possible that other people are talking about exactly the same thing, but using other terms, and I haven't discovered what it is. But for now, I'm going to use the term representational information. And the goal to me of thinking about things in terms of representational information is that we want to maximize the interpretability of the structure. This is what we gain from thinking about things in terms of representational information, because there are multiple ways to represent the same thing, probably with the same amount of conditional complexity and the same amount of conditional surprise. There are different representations you can build, which would have identical conditional complexity and conditional surprise from a particular point of view. And the advantage of maximizing structural interpretability is that it helps you in this other task, which is maximizing your generalization ability. So you can think of generalization in two different ways. One is that you can generalize to new data sets, right? You give me a new data set and it works. You give me something which has not been part of the training sample. That's a particular kind of generalizability. But another kind of generalizability is that you can generalize to different situations. You might learn something in hydrology and apply it in economics, or vice versa, or something like that. So the domain shifts quite a bit more. It's not just spatiotemporal generalization. It's actually generalization across problem domains. In some sense, you can think of physics as being the science of trying to build the ultimate generalized ability, because it applies to everything, no matter what perspective you take. Yeah. And so what that means is, we'll come back to abstraction in a minute, but that sort of interpretability then allows you to transfer knowledge across domains. Okay. So that's sort of my perspective. Okay. And then I also thought to I always love to do this, build a definition of something based on my current understanding. It pushes my limits. And so I'm calling this goal of science, or you might call it the goal of modeling. And here's what I think it is. The goal of science or modeling is to discover a representation, including its embedding. Okay, we need to talk about what an embedding is. That is interpretable and minimal description length, and that results in minimal predictive surprise and generalizes well when tested against reality. So that's kind of my attempt to compress science down into the smallest number of words, definition of science. And if you guys have any feedback on that, I'd love to hear it. So the idea is we've got something happening. We've got some data in the world. We want to model it. We want to explain it. We have to use the way we do that is by building a representation of some kind. We'll talk about how we do that. And then we want that representation to be minimal description length for the reasons that Solomonov and Kolmogorov argued for it. And we want it to be interpretable for the reasons that I'm arguing for it, that you want to be able to generalize across domains and so on. And then using Shannon's argument, you wanted to have minimal predictive surprise because you want it to be the best possible model you can get, right? The best compression, and then anything that's left is completely unpredictable, but you want the entropy of that unpredictability part to be as small as possible. And then I explained why I think it should be generalizing well when tested against reality. Okay. All right. So with that background, this is what I think of as the general problem. We want to somehow learn, and learning is from both data and theory. I'm going to argue and happy if anybody wants to argue back, that you cannot actually learn with only data or only theory. You have to have both data and theory. Okay. More specifically, we want to construct some representations or models that characterize system dynamics. So I'm interested in the dynamical problem. There's a simpler problem, which is just the classification problem, or a regression problem, where you just say, if I see X, what do I get? I just get Y, something like that. But here I'm thinking in terms of problem we're all interested in, which is how does the world evolve? Mainly because as organisms, we have to make predictions in order to survive. Okay. And in the context of geosciences, for me, mostly hydrology, we want to be able to use these representations that characterize system dynamics to generalize across space and time. So, for example, we might want to do catchment scale prediction of stream flow in response to mass and energy drivers. We may want to characterize the dominant processes governing input state output dynamics. We want to learn a generic enough representation from large data sets, sort of the thing that machine learning has now been doing with Freddie, extending on Freddie's work. We want to be able to regionalize to enable prediction at ungauged locations, that's the space. We want to generalize to enable prediction on the changing climate and or land use, that's time. And we want it to be interpretable to support decision-making, okay? Mm-hmm. And so one is to generalize across space and time, and then the other is to reason about causes and their potential behaviors under alternative conditions. So a part of prediction is about saying what's going to happen next, but there's a different kind of prediction, you might call it projection or scenario analysis, which says, if I changed this, what would happen? And why do we need that? Because we need to be able to, partly we want to be able to know how to respond, to minimize risk and respond to current things you haven't seen before in the past, but you can anticipate might happen, counterfactuals. And another reason is you might want to control, right? You might want to develop. So in order to develop a control system, you need to be able to reason about what would happen if I change this or I change that, because otherwise I would not be able to develop a valid control mechanism, like driving my car. For specifically, we're working in hydrology. We go from that real thing to some model representation of it. So there's my conceptual representation of it in terms of all the things I think that are maybe important. And then I go ahead and I built this sort of graph, directed graph-like. It's not exactly, almost towards a directed graph-like representation of it. And that's a representation, okay? And then I can go even further. And so that's the problem domain. And then the generalization problem is I might have data in specific locations in space and time, and I want to be able to learn from some of those locations and generalize to others. So for example, the prediction on gauge basins problem. Okay. So we want to build representations. And here are what I think of as some of the desirable attributes. One is we want them to be learnable, okay? So what that means is they can be readily and progressively refined through interactions with data. So we know that our models are going to be approximate, not quite real, based on limited understanding. So as we get more data, we want them to be able to updatable, okay? We want them to be regionalizable or generalizable or transferable. So somehow you must be able to adjust them in a predictable way to represent different classes of similar but different dynamical systems within some broader set. Okay. Let me start with a simple example, and then we can generalize it to hydrology. For example, when you do classification, you want to be able to recognize cats from dogs. But once you recognize cats, you might want to be able to subdivide into types of cats. Instead of thinking about cats, let's think of cat behavior. So dynamics would be cat behavior, and different kinds of cat behavior, like different kinds of cats, presumably, would be the different kinds of dynamical systems within the class of dynamical systems. Okay. So we want a general strategy for building models of dynamical systems But then we also want to be able to restrict those to particular classes so that we can make predictions about under what conditions do I need this kind of system versus that kind of system. What are the differences between them? So that might be, for example, dynamical behaviors of arid catchments versus humid catchments versus grassland catchments versus alpine catchments versus something else, okay? So somehow, as we build that model, we want to be able to recognize in what geoscientific context that class is applicable. And then we want it to be interpretable. And the question is, what does this mean, okay? So to me, these are the three key things. The model, the representation should be learnable. It should be somehow classifiable into subclasses so that you can use it to generalize or transfer. And it needs to be interpretable in some sense so that you can use it for reasoning and some of the other things I mentioned earlier. So what does interpretable mean? And is this the same as explainable? And I don't think so. Okay, but let's talk about that a little bit. And then the question is, what is the relationship of interpretability to reasoning? Because I'm going to argue that, yes, we use models for prediction, but in your heads, you largely use them in the context of reasoning. So if something is happening, you're probably not incredibly good at telling me precisely what the temperature is going to be tomorrow. But because you have the ability to reason, you might be able to tell me whether it's going to be higher than today. And you might be able to tell me whether it's going on an increasing trend or a decreasing trend, or is it going to be cyclical with a sinusoidal pattern or something like that, right? So that's kind of the kind of things we do with reasoning. And so, in other words, they're not quite as precise and accurate, but they are more general in the sense that they talk about the patterns of behaviors rather than the specific values that you're actually going to get. Okay. All right. So here's my take on interpretability. What does it mean for a representation to be interpretable? I'm going to argue that for anything to be interpretable by me, it has to be based in a language that somehow makes sense to me. If you talk to me in Chinese, and I've never studied Chinese, it's just not going to be interpretable. I'm not going to be able to understand what you're saying, and I'm not going to be able to make any sense of it, do any kind of reasoning or interpretation. So it has to be a language that somehow makes sense to me. And what's a language? A language is constructed by, this is the information theory context. You have an alphabet of symbols that you give precise interpretations. You then create a dictionary of words from those symbols that have semantic meaning, and you end up with a vocabulary. And then you establish some grammatical rules which govern the syntax of how you combine those symbols and words. In other words, there's some allowable operations, and you use those to form sentences or do operations, or transfer between one thing and another, or relate one thing to another, and so on. But I like the analogy of thinking about language because it's one that's easy for us to understand. I mean, think about it as English or something like that. Of course, math is a language too. Math has an alphabet of symbols that are precise, that you give precise interpretations. You create words and you create vocabulary in math, and then you have grammatical rules like addition and subtraction and all these other things, you know, basic foundations of mathematics. And then once you've got that language, any representation that we build is actually just a description constructed using that language. And then it's interpretable in the context of that language. So if I build a description using words, that's one kind of description. If I use a description using, if I build a description using English language, that's one kind of representation. If I build a description using mathematical symbology and language, that's a different kind of representation, okay? And the math one is interpretable in the context of math language. Of course, there's an overlap between English and math. I'm not saying these are completely distinct. Yeah. And when we get there, we then also have to talk about this concept of abstraction. So what is abstraction? Abstraction is a process, I think, whereby you take grammatically valid combinations of symbols, sentences, and you replace them with single words or symbols. So I've got a long thing which describes it in detail, and I give it a single word and I call it a cat. Okay, and that's an abstraction. And what that means is I'm being less precise, but I'm being more general. Okay. And now, instead of every time I want to talk about a cat, talk about ears, whiskers, pointy nose, forelegs, hair, and long tail, and so on, I just use the word cat, and I add that to my dictionary. And now I can talk about the behaviors of cats, or my cat, or what she did yesterday, or whatever, without having to describe to you what exactly a cat is, right? I've added it to my dictionary. And you can think in general in terms of cats without referring to a specific cat. So that's abstraction. And then you can do this with various levels of hierarchy. So by hierarchical repetition, you can construct very high-level descriptions, okay, that facilitate very, very high-level abstractions. Another way to think of this is when we initially built computers, you could think of them as basically just bits and logic gates and so on. And you had to speak to them in binary. So you had to understand the language of computers. And then somebody said, well, no, let's use hexadecimal. It makes things easier. And so then you talk to them in hexadecimal. And then finally, somebody invented an operating system which allowed you to use, BASIC and then higher level. And now you can actually use point and screen on your computer. So we have done this progressive process of abstraction to make computers easier and easier for us to use. By having some consensus as to what certain symbols or certain operations or certain kinds of things mean when I do them, right? When I represent them at that higher level. And so if I'm intimately familiar with the language and all of its levels of abstraction, then any description constructed using that language will in principle be interpretable by me. Okay, so that's my claim. Okay. If I want to speak at the level of binary, then it's interpretable at the level of binary using the language and the dictionary of binary. But if I'm using English, then it's interpretable at that level. If I'm using Chinese, if I'm talking hydrology, we invent a language in hydrology which allows us to speak to other hydrologists. But if I'm a psychologist, I invent a different language and I use it to speak to psychologists and so on. Okay. Okay, useful to think about some properties of abstraction. So one of the reasons I think that we do abstraction is from an information theory point of view, is that when we do abstraction, we end up with a conditionally simpler representation. And this is part of the problem of, why did I come to this was partly because I was trying to understand how do you do description length? How do I come up with description length of something so I can compare two descriptions and say, this is a shorter description than that? And one of the problems, which actually I think was referred to by Kolmogorov and Solomonov and others, was that your representations are always conditional. Okay? They're conditional on a particular language, a particular Turing machine that you happen to use, and that Turing machine operates using a particular operating system. And so based on the language that I'm using, my description can be a very short description or it can be a very long description. Okay. If I want to describe it in terms of bits, binary bits, it's probably much longer than if I want to describe it in terms of a simple set of concepts. Okay. And so we get this conditionally simpler representation, which enables more efficient representation communication, facilitates high-level thinking and reasoning. It allows you to do analogical comparisons, because what happens at a higher level is, because you're throwing away the details, you're comparing things only in terms of the most essential attributes that you need to compare them to. If you want to compare cats and dogs, then you just will compare them in terms of how many legs they have and, the mouth and shape of the mouth, shape of the nose, whether they have whiskers or not, so on. Okay. And so from one point of view, a cat is just like a dog, okay? But from a different point of view, it's not. By doing abstraction, you can reduce the storage of memory requirements, and essentially you can speed up computation because you've got fewer symbols to process using less memory and less operations. It can also bring about a sort of a flexibility of representation. So for example, you've got representation for prediction and control. In a particular way of representation, the full level of operational precision can be maintained even though the details are hidden from view. So this can be very useful for performing predictional control tasks where accuracy and precision are critical. An example of this would be choosing a machine learning representation of your data. Okay. So we know from machine learning that we can build models which are much more accurate and precise within sample of data, and we can extract these models from large data sets. They're very good at doing prediction and control, much better than a conceptual representation, which is based on incomplete theory.
Yeah.
Sorry, question? No? Okay.
When did you send?
I'm sorry, was there a question? No, okay. The other way you can think about it is that you can build a representation which is better for understanding and for generalization. So instead of constructing a representation with the full level of operational detail and showing it to you, I can discard a lot of the details and retain only the relevant essence of a representation. And then this can be useful for performing tasks like understanding, projection, transfer learning. And all I'm doing then is looking at general behaviors. I'm not saying exactly. So instead of being able to tell you exactly what streamflow is tomorrow, I'm going to tell you that streamflow is on an increasing trend or a decreasing trend or a cyclical trend or something like that. Okay. And the difference between these kinds of representations is the sort of level of complexity of the description. So you can take the first representation and you can simplify the description. You can throw away things that are not, and as you throw away as you throw away description length, as you go to shorter and shorter descriptions through abstraction and various other things, you may end up with a model that is not quite as precise. Now, obviously, in physics, we're trying to do both, right? We're trying to build a representation that is both good at understanding and generalization and good for prediction and control. So presumably, there's some sweet spot in the middle that one is trying to shoot for also. The other thing that I think we have to recognize is that anytime we build a language, it's really, what is it really? It's a system of encoding and decoding. In other words, if there's a description, which is an encoding in some language, if I know how to decode that description, then I can, in principle, interpret it. So I send you a coded message. It's in some description, but now I have the decoder, and that decoder is my interpreter. In a computer, it's called an interpreter, and it basically converts it from whatever coded system of symbols I've used back into the language that I can understand, and then I can interpret it. Right? So you want to send me a message, and you want to do it efficiently. How do we do that? This is what Shannon worked on. You convert that language into bit strings, you send it over the channel, and then you get it back, and I use the decoder to decode it back into the original, the language, or you could decode it into some other language, right, with a proper translator. But to do that, I need to be intimately familiar with the alphabet of symbols, the dictionary words, and the grammatical rules that govern that syntax. If I want to decode a description in one language into another language, I need a translation dictionary. And so that means I need to be able to set up a mapping from the symbols, words, and grammatical rules of one language to the symbol, words, and grammatical rules of another language. Okay? Large language models have been doing something like this. And the interesting thing to recognize here is that if you can't establish a perfect mapping, one-to-one mapping, if that doesn't exist, then information can be lost during translation. And one example might be that if you use more symbols and words and so on, as you might do in Chinese, for example, the alphabet is much larger than in English, then in principle, it's quite possible, I'm not saying it actually happens, but it's quite possible that information might be lost in the translation from one language to another. And so it might be, if you have more symbols and more words and more complex grammatical rules, you'll be able to express more complicated thoughts or ideas than you can with a simpler language and so on. Or you'll be able, or you may need to do a lot more operations in that simpler language to express something that's represented in this more complex language. And so constructing a representation is just a process of encoding using some selected language, okay? That means, well, that starts with compiling data. That means you take data and then you encode information about the world. Then you build dynamical systems models to encode information about relationships between input states and outputs. We do that in the form of equations or algorithms that operate on variables. That's the particular encoding we use. And then we use that dynamical systems model to operate on inputs. And the model then encodes the inputs in terms of states, and then we decode the states in terms of outputs. Okay. So there are many ways to see how this analogy of encoding and decoding works. You can apply it at different levels of abstraction. Of course, the choice of embedding is important. What is an embedding? An embedding is a particular choice about how we represent or encode relevant information. Okay. So think about probably the simplest way to explain this would be large language models. In order to represent language so that it can be computed using a computer which only understands bits, you have to take the words in the English language, the alphabet, and you have to represent, one way of representing that is using vector spaces. So you take every word, you use one hot encoding, and you convert it down to, say, a 512 dimensional space. So every word occupies a location in 512 dimensional space. It's got 512 numbers associated with it. And then you learn the embedding that allows you to do semantic operations, meaning, which gives meaning to those vectors. So that if I add the vector for man and royalty, I get the vector for king, all these kinds of things, okay? So that embedding is really just a way of taking things in the world, of which there are countless, and representing them in some lower dimensional space. Now I can do one hot encoding for that, or I can use some vector type of encoding, which is what we typically do, okay? So hopefully that makes sense. The important thing about embeddings is depending on the problem that you want to solve, the embedding needs to be able to represent all of the important essential information that is relevant to solving that problem. So if I want to build graph neural networks, I would have to use a different kind of embedding than if I want to use a standard machine learning neural network. And in fact, they have to construct different embeddings because they have to represent both nodes and edges and links and so on using vectors in a graph neural network. So the choice of embedding is important. It facilitates ease of communication. If you choose an embedding that makes it hard for you to compute, you're going to be very frustrated. So you're going to choose the one that makes it most easy for you to compute answers. It facilitates similarity assessment. So in large language models, the primary operation is a dot product operation. You take two vectors and you do a dot product operation to check how similar they are. So two words which have similar meaning, therefore occupy very similar space, locations in vector space. And that's done by ensuring that the dot product between those two words is as small as possible. And words which have to be very different meaning have to have very large dot products. Like you can have so the angle has to be as small as possible, which means the dot product has to be 1. And the exact opposite would have a dot product of -1, right? And you have all the other possibilities. Oh, I just said this. Machine learning typically implements vector space embedding, which facilitates vector space operations. And in transformers, they do that using tokens, right? So this is basically what I just said. And I also just said that. Sorry, can't get into detail, but I was reading up about graph neural networks, learning about them. And one of the things they emphasized there was that in order to be able to do the standard kinds of machine learning operations on graphs, you had to construct a different kind of embedding where the operations of addition and subtraction and dot product and so on made sense in the context of graph neural networks. Okay. All right. So physics-based modeling and machine learning-based modeling use closely related but slightly different languages. They're similar in the sense that both languages encode the system using directed graphs, nodes and links. In other words, they represent things in terms of objects and relationships. Both use the same basic mathematical operations of addition, subtraction, multiplication, division, and so on. But the differences are that machine learning typically has a lot more flexibility in the receptive field. So what do I mean by that? That means that when you build a model, you're in principle allowed to use anything that is informative about the thing you're trying to predict. So let's say you're trying to predict stream flow, and you go out and you collect data about sunspot numbers or the economy or something like that. And if using information about the economic index is useful for predicting stream flow, then in principle, you can just toss it into a machine learning model and you can use it because it doesn't require that the internal states of the system obey mass and energy conservation, right? All that they require is that they're informationally relevant. Okay. So the receptive field for a machine learning model is in principle much larger. And the other difference is that the allowable operations, the dictionary of allowable operations tends to be different. So in machine learning, we're typically limited to some very basic ones. And the idea is that from these basic ones, we can construct more complex ones. So we're typically limited to linear affine transformations, which use multiplication, addition, and summation. Monotonic nonlinear transformations like sigmoids, ReLus, tan hyperbolics. And then we do normalization, for example, softmax for estimating probabilities and so on. Whereas when you look at the language used by physics-based modeling, it's typically much more extensive, draws from a much larger mathematical dictionary. And for example, you use logarithms for scaling, nonlinear coordinate transformations. We can convert from Cartesian to polar. We can do trigonometric functions to represent periodicities, integration and differentiation, and so on. Now, if you say, yes, but all of those things can be represented using things like linear affine transformations and monotonic nonlinear transformations and normalization and so on, I will agree with you. It's just that a logarithm is at a higher level of abstraction. Okay, so I can use one symbol to represent a logarithm, whereas if I want to represent using machine learning, I have to use a larger number of symbols and operations to do the same thing, okay? So from this point of view, there's in principle no reason why physics-based machine learning cannot happen, right? Because all you have to do is ensure that you've got an appropriate embedding, and then you've got an appropriate set of operations, and you've got the appropriate architectures and ability to do learning by doing backpropagation or whatever the learning mechanism and so on is. And I think we all sort of intuitively understand this. Yep. It's just that when we do physics-based, we use terms that we have learned to understand as having some meaning. And so when we see a logarithm, it means something to us. When we see a nonlinear coordinate transformation, it means something else. When we see an integral sign, it means something. The machine learning model might be doing exactly the same thing, but when I look at the linear affine transformations, I would have to look at the patterns of how these linear affine transformations and ReLUs and so on are combined together and say, this pattern of doing this is equivalent to a logarithm, okay? There would have to be this translation dictionary. So, and this is what I just said, there are interesting differences in the level of abstraction. They draw on different dictionaries. There are also interesting differences in the grammatical rules. So they may have different constraints on what are allowable operations. For example, physics-based models will tend to be constrained to obey symmetry principles, like conservation of mass and energy. Whereas machine learning models tend not to distinguish between mass, energy, and information. They can implement different kinds of attention mechanisms. So what attention is how you determine how much weight or importance you give to some particular information. And modern machine learning typically implements this thing that we call context-dependent attention. Like, that's how transformers work. They attend to the previous words in the sentence, but depending on the order of the words, they apply a different kind of context dependence attention weight to each word in the sentence to predict the next word. Okay. In principle, we could apply something like that in hydrology by saying, depending on the sequence of streamflow in the past several days, and depending on the sequence of precipitation in the past several days, I could learn how to pay attention to each of those values of streamflow and precipitation and tell you a more accurate prediction of what streamflow is going to be tomorrow. Okay. They can also implement different kinds of memory mechanisms. So physics-based models tend to use Markovian memory, whereas machine learning models tend to use some combination of Markovian and sequence memory and any other kind of memory that you can invent. Yeah. And then, again, I just want to point out that these differences are not fundamentally necessary. They're just a consequence of the language that we have adopted. And the interesting thing is that we learned a language based largely in physics and statistics. And now machine learning is coming along and saying, yeah, but if you allow yourself to use a much more primitive language, you can actually do this, right? Which means removing some of the grammatical rules and constraints. The other way to think about this is that at the level of implementation, when you get to computation, both of these kinds of models, physics-based or machine learning-based representation, have to be expressed ultimately in terms of a base level set of symbols and operations that can be implemented on your computer. So ultimately, it all has to be translated back down to binary. Okay, that's another way of thinking about the fact that actually both of these are, at some level, you can make them both sort of equivalent down at some level. And if they're not equivalent, it's because somewhere along the way, we put constraints or restrictions into which operations can be performed or what is allowable. So digital computers can use a variety of languages. So you can compile programs in binary or hexadecimal or so on, or you can construct more complex operations by using Boolean logic expressions, using logic gates, not, and, or, and so on, implemented using transistors. If you go to a biological organism, they, instead of using binary and so on, they sort of do something more using sort of electrochemical components through some reflex nervous system and endocrine system. They probably still need to do some very similar operations like AND, OR, XOR, and so on, but the hardware to implement it is different. And so we have to think about the informational base. This sort of gets to Chiara Marletto's work, where she basically said all information is physical because you have to start with binary bits. But when you get to the level of hardware, computers are using with a particular kind of hardware, and biological organisms are using a different kind of hardware. But some of the things, some of the operations like logical operations apply whether you're using digital or whether you're using biological. And I said this already before, prediction and control, where accuracy and precision are important, can be mainly represented at the base level. So in a biological organism, prediction and control happens below my conscious level most of the time. Okay, I've got reflex motor loops in my system, which when it sees a particular pattern of information coming in, it knows how to control it so I don't fall down. And that's what enables me to walk. And so all I have to do is say walk, but I don't have to be consciously aware of the huge level of detail that goes on in order to control all the muscles and so on in order to walk. And I can do very accurate walking for the most part. Yeah. Or catching or throwing a ball, right? You have intuitive physics. You've got some intuitive learning in there. As a kid, you practiced throwing a ball. You didn't learn the equations of motion. You just learned that if you throw it this way, and with this kind of velocity, it'll travel this far. And then if it's windy, I have to compensate and so on and so forth. Right? So you don't have any equations in there in the sense of interpretable symbols where you can say, I'm implementing this equation. You're just really implementing some very reflex, lower level set of operations. So you can think of that as very much like machine learning. But when I want to do understanding, reasoning, or generalization, where projection is more important than prediction, then mainly that's stuff that's up here in my conscious level of mind. And that's sort of interesting to think about because people have told us, psychologists have told us that we can only represent a certain number of symbols in our head and manipulate them and do abstraction, which is why your phone numbers are only 10 digits long or, whatever. When you try to memorize something, it's very hard to memorize long sequences of symbols and operate on them. So presumably we're working at higher levels of abstraction. So at the base level, of course, everything looks like this. The Matrix movie made a big deal about this. My main point, of course, is that for a representation to be interpretable, it has to be constructed using this language that makes sense to someone. That includes an alphabet, dictionary, and grammatical rules. Any representation that we build is going to be interpretable at the level of the language used to construct it. If I construct it in binary, it's interpretable at the level of binary. So a machine learning model is interpretable at its level of abstraction using the dictionary meanings particular to the language at that level, which is why Greniering could comfortably say, hey, machine learning models are completely interpretable to me from a particular point of view. Yes. Yeah. A physics-based model typically uses a different dictionary and language and therefore interpretable in a different manner. And so I can say, yeah, but your machine learning model is not interpretable by me. Okay, but the problem is not in the machine learning model. The problem is in that I don't have the translation dictionary. So if we want to be able to interpret machine learning models in terms of geoscientific constructs, we can do one of two things. We can either construct a dictionary-to-dictionary translator that can suitably map from one level of language to another. Ultimately, I think this is going to be necessary, and ultimately that's what our computers do. Okay. For example, we have to define how a logarithm or sign operation is implemented using basic neural network operations such as linear affine transformations, rectified linear units, normalization, and so on. And it's interesting, but after I wrote this slide, I actually found a video by a guy called Miles something. I can share it with the group, where he's talking about doing exactly that. They take machine learning models, train them on data, and then they take parts of that machine learning model, which are nodes and links and so on, and then they use what they call symbolic regression to snap symbolic symbols to certain patterns of neural architectures. So that if you see a particular pattern of neural architecture, then search through these symbols and say, what it's doing over here is closest to a sign operation. What it's doing here is closest to a log operation, so on. And then they go into the neural network and they replace that that part of the network with a sign, or they replace that part of the network with a log operation and so on. And so they progressively convert the machine learning model to a more symbolic representation. And in the process of doing it, that scientific model becomes interpretable. Okay, so that's one way to do it. The other way is you just start from the beginning and you construct the model itself only using interpretable components. So you decide on what your components are going to be. And to my mind, this is sort of easier, and this is why this is the approach that I have adopted, at least for now. But I really think ultimately there's going to be a sort of fuzzy overlap between these. Okay, so so all I have to do in that case is I have to choose the objects that represent the nodes of my machine learning model, and they have to be interpretable objects. I have to choose the relationships that represent the links between the nodes, and they have to be interpretable. And now I can build a machine learning model which is constrained by these components. Okay, and I can do standard machine learning on it. So if I want to do interpretable geoscientific modeling using machine learning, I need to use physics-based models that can represent flows of mass, energy, and information, right? So they need to be representable using symbolic language, such as differential equations. The rate of change of x is some function of x, the input and some parameters. Or I can use a visual language, right? So these are the two most common languages that we use in science. We use equations and we use directed graphs. You'll notice that these are both more useful for different kinds of understanding. A directed graph helps me understand relationships in a very easy to understand, visually appealing. I can just look at it right there. I can see what's connected to what. You can do the same thing with differential equations, but you have to do a little bit more work. On the other hand, differential equations emphasize a different way of looking at the same representation. Yeah. So there's different kinds of abstraction. So I conceptualize my system with drivers, memory, some observed outputs, and some unobserved losses. And this is what I call the receptive attention field problem. We have to say, what am I going to observe? How am I going to observe it? How am I going to represent it or embed it build my representation? Once I've chosen that receptive field, it constrains my representation. And my representation entirely based on that. In machine learning, this would be the same as saying, what do I choose for my inputs and my outputs? Yeah. And how many cell states do I need? Okay. And then I can take that and I can use a directed graph representation to build some internal level of detail. Okay, so now I'm using the words in my language to construct my representation. And that's the architectural detail problem. I need to come up with a hypothesis. And then once I've done that, I've specified the architecture. My learning problem is just learning the parameters. Of course, there's a more general learning problem, which is learning the architecture. Okay. This is supposed to be a bigger presentation, so I left a blank slide here saying we need to discuss architecture learning. And really all I'm trying to say over here is that there's a different kind of methodology that I use to do parameter learning and for doing architecture learning. Architecture learning is always discrete because I have to select between discrete symbols and links. There's some fuzziness between them because you can, in principle, select a very general architecture of links and nodes, and then you can learn to throw away certain links, or you can learn to throw away certain nodes. That's sort of a very complicated way of doing it. Or you have to do neural architecture search. And you can start from very simple architectures and you can grow architectures. And that's something I'm becoming very interested in now. So in other words, you build the hypothesis. From a simpler hypothesis, you construct hypotheses and keep testing them. And you keep expanding your hypothesis until it works. The other part of this is that we have to represent these gates, which determine the functional linkages between these state variables in my architecture. And so the solution that LSTMs use is context-dependent gating, and is the same solution that Yuan adopted for his PhD research, where you basically say the rate at which things are flowing from one node to another depend on the states of those nodes and some external context, right? And you learn the form of these relationships. Of course, you end up having to put some constraints in. So if you want to do mass or energy conservation, you have to constrain the sum of these gates in any particular node to be 1, and so on and so forth, the level of detail. Okay. And then those gates depend on context, and context is basically any information that tells me how open or close the gate is at any point in time. And I learned that context. And so how could I learn that? I could use a transformer, I could use an LSTM, I could use just simple regression. There's lots of particular choices that could be made for that particular architecture. Okay. And that's what this slide is saying. Here I've got a gate. Now I've got a neural network which is learning the context-dependent gating function, and then handing off that gating, the values of those gates to my mass and energy conserving architecture representation of the system. What the interesting about this representation is now there's no parameters in this part of the representation. There's only structure or architecture. All of the parameters that would be learned are down here in this context learning part of the system. And here's some examples where we applied this kind of approach to modeling the input-output dynamics of the Leaf River Basin. So what we're showing on the y-axis here is a measure of efficiency. It happens to be kg, but it doesn't really matter, right? One is ideal performance. And what I'm comparing here, for example, is on the right over here, is I take a purely machine learning approach based on LSTMs, which are gated neural networks, okay? And there's an LSTM with 1 node, 2 nodes, 5 nodes, so increasing level of complexity. And you can see that what this says is that based on LSTMs, I can achieve an efficiency of around 0.9. And what this box plots show are I'm measuring efficiency on different years of a 40-year data set. So there's some variation in efficiency depending on how wet or dry the year is. The driest year happens to be this year, which is represented by this circle. And the wettest year is the one up here by this little bar. And the box plot just shows the distribution of performance over on an interannual basis. You can see when I go from 2 nodes to 5 nodes in the LSTM, I get some improvement, but not huge. But definitely going from 1 node to 2 nodes, I get some performance. So this blue line up here at the top is the median and interannual performance of the LSTM on the Leaf River. Okay. We tried longer with more nodes and nothing improved. So 5 was sort of approximately optimal. Okay. If I use a standard recurrent neural network that doesn't use a gated neural network architecture, you can see the performance drops. That's because you're not allowed to learn the gating as being context dependent. So it's constant gating. You just learn constant gating values. This is a model based on artificial neural networks, which is just basically nonlinear time series analysis. You can see the performance is very similar to the recurrent neural network. The other thing I should mention is all of these representations only have access to exactly the same information, okay? None of them has more or less information than any other representation. If I use a linear time series model, the performance is quite a bit worse. So clearly we need nonlinearity in the system to explain it. But here's our interpretable mass conserving architecture using a single node, but using different levels of complexity of the internal representation. And I can talk about what those are if anybody's interested. But the basic point I want to get at over here is the red line here is the median performance of our interpretable mass conserving single node architecture model. And the blue line is the LSTM, which arguably is not constrained, so it can use all of the information that's in the data optimally. And you can see we're pretty close, okay? So by giving up a little bit in terms of predictability, we now have a representation that is actually highly interpretable in this particular simple example. Need to put in some slides about why do I say it's interpretable, but I'm happy to talk about that, okay? Now, if you could do that at any particular location, you could build a model like that at any particular location, then that model is going to have this context-dependent gating is going to be made up of parameters that have to be learned by the machine learning model. Now the question will be, do these weight patterns show regional, do these weights, these sets of weights show regional patterns? And it turns out, and now I'm hand-waving a bit because I'm actually talking about work done using a different model architecture by Luis, who, is he still here?
Yes, I am.
Yeah, thank you. So I'm sort of hand-waving a little bit and abstracting here. But what Luis has shown with his hydro-LSTM architecture is that you can look at those weight patterns, and you can show that those weight patterns those weight sets have regional patterns. And so that means that you can construct a dynamical representation of a system, and then you can classify the weight patterns, and those weight patterns will be different from an arid catchment than they will be for a humid catchment or for another kind of catchment. And if you can successfully classify those, then you've basically done, you built a representation, going back to what I said at the beginning, which is a representation of a dynamical system, a very simple representation, a single state representation, for example. And now you can categorize different dynamical systems within that class of dynamical systems as being arid or grassland or humid or so on. And so here's a plot from one of Luis's papers where he's showing that when he looks at the gates of his LSTM, his hydro LSTM, the forget gate, the input gate, and the output gate, which have parameters which are the multipliers on successively lagged past information, okay, show very distinct patterns which are distinguishable across the country. I can't actually explain this graph to you very well, but if somebody wants, Luis can explain it, okay? So in other words, you could start with a representation which represents your physics of your system. You could learn the context-dependent gating mechanism, and then you could learn the classification system architecture, and that's exactly what Luis is doing now in his most recent work. And so now you have essentially the full enchilada, and in principle, you have a system that can be learned using machine learning concepts, but which is actually interpretable. At least that's sort of the big picture idea. Whether we're completely successful remains to be seen. Okay. All right, that's just what I just said. So we've got an interpretable representation which can be trained using machine learning and big data. And we've got a way of characterizing classes, dynamical systems into similar or dissimilar subclasses. The idea for how to achieve this is entirely Luis's, not mine at all. So I want to make sure he gets full credit for it. But it's a very interesting idea, in my opinion. So I'll finish here by saying, the goal of science is to discover a representation, including embedding, that is interpretable in minimal description length, and that results in minimal predictive surprise and generalizes well when tested against reality. We want our representations to be learnable, regionalizable, generalizable, and we want them to be interpretable. We have to build our representations using a relevant language if we want them to be interpretable, and we have to represent them at some appropriate level of abstraction. The level of abstraction we use will determine to some extent how accurate those models are going to be, or what the purpose for which we use those models. And okay, so thank you for listening.
Thanks. Very interesting.
Leela, I'll let you moderate questions.
Yeah. Steven, do you have a question?
Probably. I was wondering, like when you showed like these 4 components of science or models, like interpretable, description length. I'm wondering if we try to distill further, could we all see this as description length? Like in my view, like minimal predictive surprise translates very quickly to description length because you can assign code lengths based on minus log probability. So the less surprise you have, the more compression basically. But then interpretable, yeah, I have some difficulty with that. Like in my view, interpretable is minimizing the description length in the mapping from our intuition to whatever model you have. So that works well as long as our intuition is good about and we have learned stuff about the real world.
Right.
So if you see it like that, then interpretable just means that it minimizes the description length of describing our intuition given the model, or the other way around, that it minimizes the description length of the model if you take whatever we have in our intuition as a fixed given.
I think you're right at an essential level that there's fundamentally no difference between interpretability and minimum and description length, except that in depending on the language I'm using, so I'm going to say description length conditional on a language, okay? And depending on the language I'm using, I might choose to use more words than the minimum for you to understand it because you don't have a good understanding of the meaning of the words yet, right?
Yeah.
So, but if we completely agree on the meaning of the words, then minimum description length and interpretable should coincide. I think I agree with you on that. Yeah.
Yeah. So it's an efficiency thing.
Yeah. The problem is usually, but we also then have to say description length conditional on the Turing machine, right? And and so yeah, you can use Turing machines at higher level of abstractions, and so your description length will be very short because you don't have to explain to the machine certain things. But if you have to explain things to the machine, then your description length becomes longer and longer and longer. Yeah.
And since basically everything we do is about making good decisions in the world or in the universe we live in, maybe you could also see it as a mapping from like physical reality to any language. So I wonder, like with this other buildup of defining interpretable, you start with interpretable characters or interpretation of characters, but I don't think those characters can have any interpretation if there's no mapping.
There has to be a mapping.
There has to be can you with the real world basically, because right. I think you cannot build up a language in isolation of a reality that you're trying to describe.
Agreed. And you're only going to choose symbols and words which allow you to express your experience in the world.
Yeah.
So if you use binary, you're basically saying you can take any anything of interest, any variable of interest, and you can represent it in terms of 2 possibilities: left and right, up and down, 0, 1, on and off, whatever, right? I like left and right because you can think about yourself as a little bacteria or amoeba or an organism, and you're trying to eat fish, and you have to predict whether the fish is going to go left or right, right? So it's simple binary choice. I got to make that. And you have a record of data, which is in the past, did the fish go left or right, left or right, left or right, left or right? And so you got a string of symbols, 0, 1, 0, 1, 0, 0, 1, and I got to predict the next symbol.
Yeah.
Right? So that's a very simple language. It only requires binary. But I still need a minimum amount of hardware to implement that language and to store information about how many times did the fish go left in the past versus right, or if it went two lefts, did it do a right? Okay. So
Yeah.
I also agree with you that everything is ultimately down to conditional probabilities. But the part of the conditioning is what I think Kolmogorov referred to as the description length part, where you can describe the predictable part of it, right? And then you take the unpredictable part of it and then call that the conditional surprise.
Yeah.
And then you have to describe that by the probability distribution. Yeah.
Okay, that's all for now.
Okay. Thanks, Steve. I knew you'd have an interesting perspective on that. Joseph, I think you had your hand up a little while back.
I didn't, but I do have a question.
Okay, go ahead.
Yeah, in a similar way as Stephen, perhaps all these 4 points can be compressed into the umbrella of causality. But I noticed you never mentioned causality in your talk. Was that intentional, or what are your thoughts on that?
It's true I didn't mention causality. It was not intentional. But now that you mention it, I'm taking a perspective where I'm trying to start from data and I'm trying to back out what do I understand by information and models and so on. I'm trying to understand data in the context of why do I need data in the first place. And so if I just start with data, I don't need to assume causality in order to start building a representation. If I have a string of zeros and ones, all I have to do is look for patterns in that string. And then once I've extracted all possible patterns from it, I have to look for violations of the pattern, of all possible patterns. And then I have to somehow characterize the entropy of those violations. That's my surprise part. And right now, I don't need to invoke causality. But as those patterns become more complicated, it might be useful to invoke causality as a way of explaining those patterns. So that would be a higher level abstraction to me. Yeah.
Yeah. I mean, without causality, how can you generalize?
Well, right now, machine learning model, yeah. So you can do in-sample generalization, right? Machine learning models are very good at doing in-sample generalization, provided you give them the right data set, right? We call it interpolation. But when you say generalize, I think what you mean is outside of the sample. You want to generalize outside of the range.
Yeah.
Right? Mm-hmm. So to do in-sample generalization, I have to invoke smoothness and continuity. Let's leave that aside because I can't do any generalization without that. But let's say I want to go outside of the sample, then I want to say what's likely to happen under conditions I've never seen before. Now there's 2 possibilities. My data contains enough information to understand the underlying data generating mechanism. And so anything that happens outside of my sample only obeys the rules of that data generating mechanism. Or my data does not contain enough information to learn the underlying data generating mechanism. If my data does not contain enough information to learn the data generating mechanism, I need to invoke a hypothesis. So I have to add information that's not in the data. And one particular kind of useful information to invoke is causality. Right? It's an assumption about the world, so to speak. And if I test that assumption and it works really well, then I get more and more and more support for it. At least that's the way I think about it.
Yeah. I mean, the only thing I have to say about that is that kind of the entire field of causal inference is trying to learn causality from observations, right? So there are, I mean, especially when you have time series like we do in hydrology, there are lots of ways that we can kind of infer causality just from data.
Sure, but if you've if you've never seen a particular, okay, I forgot to say this. If you've never seen a particular event before, that event either obeys the rules you can learn from the data, or it does not obey the rules you can learn from the data. Okay. If the data is complete in the sense that you can learn all of the underlying rules, then yes, you can predict out of sample. In some sense, it's not really out of sample because your data contains all the rules, so you've learned all the rules, so your predictions are always going to be great. But if your data is imperfect, if it doesn't contain enough examples for you to learn all of the underlying causal principles, then you're likely to fail out of sample.
That makes sense. Thanks.
And I think this is why in machine learning, there's such a big emphasis on your data has to be fully representative of the system. Your training data has to be fully representative. Your testing data has to be fully representative. It's very hard to guarantee, but that's like the basic thing we've got to do is start with saying, can I really learn what I want to learn from this data? Or not?
Yeah, thank you, Hoshin. It was a wonderful presentation and a great discussion so far. And I always get more questions than answers, but I guess that's good. And one of the more salient questions that I have, or ideas for discussion, is this. There seems to be, from your words and from other conferences, that there are in hydrology specifically, and on some other areas perhaps, there are always multiple solutions to the same problem.
Yes.
And that means that I can get different ways to resolve the same problem via machine learning or via physics. And my intuition also says that even via physics, there may be multiple solutions to resolve the same problem. In other words, if you, yeah.
Can I pause you 1 minute?
Of course.
I don't want to interrupt what you're saying, but I just want to be clear when we say we should understand what we mean by solutions, right?
Oh, yeah. Yeah.
I think what you really meant was there are many ways to represent the same input-output relationship.
Yeah. So by solution, I mean the usual way we calibrate and validate models with certain accuracy, say above a threshold, for example, 95% of the KGE or Nash Shufflet model efficiency coefficient, we can get kind of a set of models that explain the same problem.
But I'm trying to be a little bit precise in that it may be that from here, where I am right now, to my target, it may be that there is only one path. It may be that there's only one physically realizable path from A to B, in which case there's only one solution to the problem. Okay.
Yes,
but
there may be
cases,
one solution. Yeah. Yes,
but in most cases, there are multiple paths from A to B. I think that's what.
So you mean by the path, but you mean the minimum energy or the minimum? Oh, Hoshin is gone, I guess.
I'm here.
Hoshin, are you here? Oh,
I'm here.
okay. But by the minimum by straight line, you mean the minimum energy way to get from A to B, or
no, I didn't even mean minimum. I just said it's quite possible. I have to allow for the possibility that if I want to go from A to B, there's only one way to get there. Okay. I'm not saying that's true in the world.
Yeah.
I'm saying I have to allow for that possibility. If I can eliminate that possibility, then what you're saying is actually correct, that there are many possible solutions to the problem. Okay. But in any particular situation, there may be more than one way to get from A to B.
Yeah. And I think it's context dependent and problem dependent too. For example, if you want to explain, and so my second idea, what I was talking about was, so first, there might be multiple solutions for getting from your input to your outputs for certain accuracy, and it's acceptable, and it's even transferable to other time series of related variables. So there's certain transferability that is acceptable too. But my point is, if you go back to physics, which is even a more constrained language than, I guess, machine learning, because it now has more explicit representation in physics, and the physics is very distilled from the data, there might actually be other physics explanations. And I'll give you an example. When we study the ideal gas law, so we have the pressure, volume, and temperature related. And so I can I can give you the volume in terms of temperature and pressure, or I can give you the pressure in terms of the other two variables or stuff. So what about if a machine learning model is able to distill the same, is able to tell, well, actually the driving forces are pressure and volume, and I can give you the other variable with the multiplication, or it's temperature. And so in that sense, I believe the representations in physics might not even be unique. They might actually be multiple solutions that you could derive from with the help of machine learning or something, or with a translator that help you, write that in that direction or the other direction. So that was the context of my idea.
That's wonderful. That's a great comment. I agree with you. I mean, the fact that we cannot describe the results of experiments with light using just particles, we describe it as particle or wave, depending on the context, shows, an example of what you were just talking about. It's also true that people have been trying to use machine learning and symbolic regression to learn physics from data. A lot of papers out there. And one of the things that's interesting about them is that as they learn more and more complex representations, symbolic regression, using the symbolic language of all the things that we can use in physics-based models, you end up with a Pareto optimum, where you end up very often where you can build a more complex representation, which has higher accuracy. Okay. And at some point you have to decide, well, it's getting more and more accurate, but it's becoming harder and harder for me to interpret.
Yeah, to interpret, that's right. Yeah, exactly. But at least I think there is, so linking this back, and I'll shut up to let the others talk, but linking it back to your idea of the description length, I think there needs to be a definition of what description length is in terms of what's the accuracy that you want to describe your phenomenon with. What's the overall goal?
Yes.
With your data limitations. What's your goal?
So let me make a comment about that.
Sure.
Is that when you make a description, you actually have to quantize the world. And so your representation can only function at a certain level of quantization. I mean, Stephen has shown this nicely in his papers when he tries to do his information theory analysis. And if you use a higher level of quantization, in principle, you could get a higher level of accuracy, right? Yeah. But we're unavoidably limited by the level of quantization, which is why your computers now have gone from 8-bit precision to 16-bit precision, to 32 to 64-bit precision, right? But ultimately, when you look at how they encode numbers in 64-bit precision, there's a level of accuracy you cannot get because you're limited by 64-bit precision, right?
True.
Yeah.
True. All right, I'll shut up now.
Danielle, you've been waiting a long time.
Sorry. Thank you very much, Hoshin. Thank you for the talk. It's something that I've been thinking about for a long time, probably from very basic levels. And so the question that in the comments that I have is pretty basic, but I'm building up on Joseph and Hernan's point. Because I was also sort of surprised you never mentioned causality throughout your talk. But then all throughout I could hear information theory language as well. But I've been thinking of interpretability, and it seems to me that with this, with the development in machine learning and physics-based models, which seems to look like a competition, it begs the question whether, and I probably saw it in your slide as well, whether we should be thinking of two sides of addressing a problem in terms of a predictive. I think this is from the paper by Ben Ruddle and Gray Niren, where they speak of looking at the structural performance of the model, and so not just looking at the predictive performance, but also considering the functional one. And so I was quite happy that I saw that you were talking about the functional performance as well. But in that way, and sort of chipping from Hernan's question, where we say something like there are multiple solutions to a problem, maybe that is correct in terms of the predictive performance of the model. But then when you couple that with the functional performance or the functional error, then it would probably converge to what you said, as in there is only one way. And when I think of interpretability, I think of the convergence of these two sides, so that the goal is not just to hit the predicted value, but also to make sure that we are getting the right answers from the right reasons. And in this way, it's difficult for me to envision that without causality. At least it was for a while, until a while back, while I thought a lot about random forests and what they were really doing, which is really reducing entropy. I felt that, well, maybe the heart of it isn't causality, but the heart of it is really entropy reduction, which if I have something like a transfer entropy, I could do, or Shannon's mutual information could help me to do that. So I was just thinking of how you also thought about this in terms of how interpretability should be defined.
Sure.
Thank you. Yeah.
Thanks for that. The first thing I want to say is, let's just start with a standard machine learning representation, okay? If you let me go from there. If I have a standard machine learning representation, basically, what is a machine learning representation? It's basically a set of vector transformations from input to output, okay? With certain operations that you're doing on it, okay? Any vector can be represented, is represented using a coordinate system, okay? So a vector x, y, z. Now that coordinate system can be rotated or its origin shifted in an infinite number of ways, okay? What that means is that because there's an infinite set of coordinate systems and origins, the exact same mapping, vector mapping from input to output, can be constructed using machine learning model using an infinite number of models. In other words, you just take any representation and then you do a coordinate rotation and you have exactly the same representation, okay? But sorry, you have exactly the same mapping from input to output, but the representation is different because I'm using a different coordinate system, okay? It's kind of like I'm using a slightly different language, okay? So that's where the infinite number of ways of representing something comes from, okay? The exact same mapping, I just have to change my language slightly and I get a different representation, okay? All right. My view on causality is that I don't start by assuming that causality is true, just like I don't start by assuming that any explanation is true. What I do is I say, I'm going to take causality as a hypothesis. And if it's a good hypothesis, then it's going to help me, it's going to help reduce in that set of infinite number of transformations, is going to reduce them to only a few. And if if that hypothesis works well, then every time I'll be able to build my model using a representation based on that hypothesis, and it's going to be much easier for me to do it. I'm going to have shorter description lengths. I'm going to have better surprise metrics, and so on and so forth. So from what I gather, the history of human beings exploring the universe have concluded that causality is a fact of nature, right? And that's because doing this in many, many situations, it's always tends to be supported by the evidence. And so then it becomes a good hypothesis to use, right? So that's my perspective. It's not that I've got anything against causality. It's just that I want it to come out of the data. And if it can't come out of the data, like for example, Joseph asked, what do I do when I want to predict an out-of-sample event, right? If causality helps me to predict an out-of-sample event, that's great, right? Something I haven't seen in my data. Yeah. Hopefully that makes sense.
Thank you.
Yeah,
it did. It also sort of reminds me of Judeo-Pero's hierarchy of causality, and he did speak about this. He did say that to get to interpretability, we'll have to get to the highest part of the hierarchy, which he was talking about moving from associations into a sort of a causal framework. But yeah, it's certainly what he said makes sense. Thank you very much. Yeah.
It just occurred to me when you said that also has some connection to Kolmogorov complexity, because Kolmogorov complexity is about determinism, right? Establishing the deterministic part of the pattern in the data. And you could say causality is that pattern, right? Yeah.
Thank you. Thank you very much.
I think Leela, you had your hand up next.
Yes, thank you. Yeah, thank you for the great talk and for the discussion so far. I actually had the sense that when you were referring to Granger causality, I think it was in your slide 20, because you talk about the model to be able to represent dynamical flows of mass, energy, and information. And ultimately, that is how we have been understanding causality, like finding those, I think it was in the 20, finding those paths and nodes that connect and better represent as a direct graph all the possible connections, and ultimately that is our perception of causality. So I think it was implicit, but maybe it was biased to me. So yeah. And also in the slide 27, I noticed that when you were describing the system architecture, you were also implicitly saying that it should be acyclic, your direct graph, so that the past only informs the future. And but then it led me to think on the levels of abstraction that you want to represent with this. And so I have a question regarding the levels of abstraction. So by levels of abstraction, do you refer to how complex is the description of your system when you try to describe a certain functionality? So for instance, if you have your catchments, then the functionality is to route all the water out of the basin, right? So you're trying to predict water level at a certain point in your catchment. Or maybe levels of abstraction refers to the scale at which your model is able to represent the dynamics. So I was confused about if it was most, yeah.
Yeah, obviously I was not being precise about my abstractions here. The first thing, the only reason I'm using directed acyclic graphs is just because that's what I'm familiar with. Okay, that's not to say that one couldn't build similar things with bidirectional graphs or cyclic graphs or something. It's just I don't understand them, so I'm using the language I understand. Okay. In terms of abstraction, here what I'm saying is that I have assigned a functional representation to each node, and then I'm just going to call it a node. And the moment I call it a node, I'm going to call it an MCP, or mass conserving node, or an energy conserving node. I no longer have to describe all of its details to you. But if you really want to understand it and implement it in a computer, you need all those details.
Right.
Right. Yeah.
Yeah.
So I'm showing you a high level abstraction, which is a conceptual diagram of something which maybe one day I'll be able to give this to ChatGPT and it'll build me the model, right? That would be ideal. And with the new, is it Sora? No, ChatGPT 4.0, maybe something like this is going to be possible, where you can actually draw a diagram and say, I want a computer program that does this. And it'll say, okay, but you haven't told me the details of this. So you'll say, go look up this paper and build a node using the math that was in that paper, and so on and so forth, right? I mean, I can imagine something like this in the future. But clearly, at the level of abstraction, I've had to avoid giving you a whole bunch of details. And so there are things that you and I are having to assume in order to be able to understand and interpret this.
But I guess that is what you want to do with data, that you're gonna be increasing your dictionary to a point where it's so complex that it will be able to predict any output.
Well, it depends on whether I want to predict any output or whether I want to be able to predict trends. That's the distinction I was trying to make between reasoning versus accurate prediction, right?
Yeah.
So I think of reasoning being, I want to do prediction, but not at a fine level of detail, right?
So the ultimate goal of the model is not to be precise in the prediction, but more interpretable.
Well, I want to balance the two.
Okay.
Okay. If I take my model to a bunch of stakeholders, I have to describe the model at a level of abstraction that allows me to talk to them and to have them gain credibility and trust in my model. Okay. But if I want to use it to actually predict flow, I need to build it at the level of detail needed to predict flow. So I could still build my model at that fine level of detail, which needed at that huge level of detail to predict flow. But when I talk to you about it, I'm going to have to abstract. So I'm going to have multiple levels of abstraction depending on who I'm talking to. And some of those might be computational in the sense of allow me to predict. And some of those might be not quite so accurate, but they allow me to reason.
Yeah, I agree. A balance between the two is what it's going to make it successful. So everyone can understand it.
I don't think you need a balance. I think ultimately you need a telescopic, I think ultimately we need models which are telescopically interpretable. Okay. I think that's what human beings do. We build models for prediction, and then when you're asked to explain them, you abstract them when you want to talk about them. That doesn't mean you give up your prediction ability. But if you were to build the model at that higher level of abstraction, it would not have the level of predictability that your low level representation would have.
Yeah, I like that simile, the telescopic view. Cool. I'm gonna let Joseph go first, and later I will read a question by Manuel.
Okay, thanks.
Yeah. Dr. Gupta, have you heard of the Markov blanket?
Markov blanket. No,
Yeah.
please tell me about it.
Okay. I just showed the link, but basically I think the Markov blanket, if you're going back to the 4 goals of science, I think those goals are actually satisfied by the Markov blanket. Like if a model satisfied the Markov blanket, then the model would satisfy their goals. But to me, the goal of science is more to learn the structural causal model. So having each node as a learnable function of its parents and plus noise, and not functions of its child or husband or wife, because
So you would add another bullet point here, which would be in my list of bullet points. You would add causal to interpretable and minimal description.
I think so, yeah.
Yeah, fair enough. Fair enough.
Because the child of some node can help you predict, can minimize predictive surprise, and it's, you know, can still be interpretable. It can still generalize, but
so causality then would be a specific kind of interpretability, right? It would be a restriction on interpretability. Interpretable would be more general, I think, is what you're saying, and causal would be more specific.
Yeah, I mean, I think causality has to do with all of these points, so it's hard to pinpoint one of them, but yeah.
Well, they're not independent. Yeah, I agree with that. Because, I mean, Solomonov and Kolmogorov argued that minimal description and minimal predictive surprise were related, right? And that's what Stephen said earlier, right?
Yeah, and you can even differentiate between like wife or husband, which can give you information about yourself given your child, versus blood relatives by using data. So it's not like it's outside of data and you need assumptions. So it's
the thing I wonder about is to what extent the goal of and if I step back and say, what is the goal of science, right? If your goal is very limited to predicting stream flow, you know, it's going to be different than if your goal is to explain all observable phenomena.
right. But if it's about predicting stream flow, I'd say that's engineering. Science.
Okay, fair
engineering,
enough.
I don't think has to include causality, but if it's science, I think it would. Yeah, that's
okay. So you would argue causality in there, and also that the goal is to basically explain any and all observable phenomena.
No, just understand the structural causal model, SCM. So that's the each node has a corresponding function, and the function is of its direct parents plus some noise. And that learning that function, whether it be like parameter estimation or, as you talked about, the structure itself of that function, that would be the goal, I'd say.
Okay, so I think we're agreeing, because you're on the side of the fence which says understanding is more important than prediction, and that the way you know you have understanding is if you can do good prediction. Whereas the predictive argument is,
but sometimes you might get in trouble with prediction because children can help you predict. So that's my point.
Yeah.
So there's some Pareto thing, that some trade-off.
Sure. Yeah, the engineering argument would be we only care about prediction, and if you do good prediction, that means you understood everything.
Yeah.
So you know, you end up with this chicken and egg kind of back and forth, which is why I think you have theoretical physics and you have experimental physics, and you can't do physics without both. Thank you. That's interesting. Yeah, I'm going to think more about the causal thing.
Yeah, to add to that, I think it's a common practice to apply a Markov property when you are using directed acyclic graphs, just because otherwise you are going to end up having so many parents and children that your dimensionality increases so much that you are not able to handle it all.
So here's the thing about Markov processes. I agree in principle, but your state has to be completely informative about the past.
Mm-hmm.
Okay.
Agree.
And so the dimension of your state can be huge.
Yes.
And very often we use shorter, smaller numbers of states, which means we're kind of like we could potentially be throwing away information about the past. But if you can argue that the entire past is summarized by these 4 states, which means that once I know these 4 states, I could have come to it from many different possible paths in the past. But once I've gotten here, it doesn't matter what those paths were. The future doesn't depend on which path I came by. Yeah, then I'm good. Then I can just throw away everything and I can just use 4 states.
Exactly.
But usually we're building models using limited data, so we never actually know. We only have a guesstimate, and we use the smallest number of states that allows us to get away with it. And then tomorrow something happens and you go, oh shit, I wish I'd kept track of this one event that happened in 1959. So now I'm going to create another state to track things that happened in 1959. Yeah.
Okay, I'm gonna read Manuel's question. It's on slide 10. He says, I felt that there was an implied, I'm gonna let the
Getting there.
yes. So in slide 10, he says, I felt that there was an implied trade-off between the 2 types of representations introduced, prediction control and understanding generalization. Is this the case? Or is a representation that offers prediction and understanding still possible?
So I think when I was writing the slide, I was implying a trade-off. And so when I spoke it, I may have been also implying that trade-off. But I think I also said at one point that you can have a telescopic series. Well, I said to you, you can have this representation that does prediction and control, very accurate. But then when you want to talk about it, think about it, you can build higher level representations that throw away some detail or we chunk things. So in that sense, it's not necessarily a trade-off that I have to give up one in order to get the other. But I think that we're not yet, as a community, we have not yet recognized that what we need to do is build models that have this telescopic property. I've never seen such a model. Or if I have, I can't remember. It's not common practice, is what I'm trying to say. But I think we do it as humans.
Yes.
Yeah. So I can see a future for modeling which is based on that sort of acknowledgement. And I think artificial intelligence, general artificial intelligence, is likely to have that kind of property.
I think Hernan has a comment on that, and I think it links very well to this discussion. Hernan?
Yeah, I just posted, and we don't need to answer this in case we're getting out of time, but for the comments that I keep hearing from everybody, it seems like we probably need to define better the terms causality, connectivity, and association, and establish similarities and differences, both in time and space. And I don't know if that is connected to the
You're referring
proper
to
representation.
You're referring to the ambiguity of language, of the use of symbols, right?
Exactly, yeah. Because I see it represented in your slides, but then Lila interpreted it as an acyclic graph that she also could interpret as a causality graph. And then another person said, oh, that might actually be association. And I don't know. So we probably need better definitions or something that let us, because if we define that, the moment we do that, we probably establish better representation of the architectures that we need to use for the predictions.
Well, to give you a concrete example, we talk about soil moisture.
Yeah.
Right. And soil moisture is completely abstract concept. Right. One person might be referring to the aggregate soil, the aggregate water content of the top 5 centimeters. Somebody else might be using the term to represent something completely different. So, but somehow we managed to get by using those terms, and we kind of understand each other, right? But if I ask you, but if I ask you to take a word, I'm going to choose a very unfair word, okay? But just as an example, if I ask you to take the word love and give me 10 synonyms for love, okay, it's a very high level abstraction, right? So that's why it's unfair. And if I take 10 people in the room and I ask them to construct 10 words that are synonyms for love, and I've actually done this in a workshop once, very few of the words will overlap amongst the 10 people.
Interesting.
And then you go, how the hell do we understand each other if we have all these different
levels of abstraction and interpretation? Yeah.
But there's some way in which, in a large language model sense, all those words have similar locations in the vector space. So whether you use one or the other to do your operation, your mathematical computation, you'd arrive more or less at the same place in the vector space. It doesn't matter because they're kind of this, they're almost replacements for each other.
I mean, in causality, there's specific definitions like association. If you're given a directed or a graph, then any blood-related relative of some node, if you treat it as a family tree, is said to be associated with the given node. And then the causality is just the parents. So.
Well, the nice thing about math as a language is it's incredibly precise. Otherwise, it wouldn't work very well. Yeah. But it's good for doing certain things. It's hard. It's not as good for describing emotions and abstract. Maybe one day it will be. But large language models are getting better at recognizing people's emotions, right, and distinguishing between mildly ticked off and really pissed off, for example.
Hoshin, Alison left, but she left a very interesting comment about how her 1-year-old is learning abstraction and how he recognizes all men like a papa, as all men are all papas and all brown hair women are mommy. And so she says that maybe knowing one specific thing and thinking that it is causal and creating a general rule and applying it might be dangerous.
Yeah, perfect. Great comment. I think of this as the overfitting problem, right? Yeah, you're biased towards one particular explanation and the data supports your explanation. So it reinforces your particular view of the world.
Exactly.
And you don't have enough contrary evidence to cause you to question your model. I mean, eventually, I'm assuming your kid will stop doing that.
Yes. Okay. Right.
I mean, one of the nice things I think I learned from Stephen early on was that the nice thing about using description length as a basis for choosing representations is that as you get more data, your description length can increase. So you're never assuming that you know exactly what the correct description length is. You're just choosing the minimal one for now. And as you get more and more data, in principle, your description length would increase, and hopefully it tapers off at some point. But we never actually can guarantee that that's true.
Okay, so if we don't have any other comment or question, I think, we have covered 2 hours. Thank you so much, Hoshin, for this great discussion. And any other comments or questions?
You might want to mention what the next, what's happening through the summer, just so we know. Yeah.
Okay, let me go back to that. 1 sec. I think we have presentation in 3 weeks. So it's gonna be on June 12th, Julie May from the University of Waterloo. She's gonna be presenting signatures and processes, or a brief history of model intercomparison and studies. So yeah, we are gonna have that presentation on June 12th.
So we have people booked through the summer, pretty much?
Yes. Yes.
Okay, excellent.
We are all booked. Yeah, to the whole year.
All right. Good. So I think the next time I see you guys, I will probably be in Spain then. Oh no,
Okay.
some of us are going to be next week at HydroML, so or maybe a lot of us. So, all right. Andrew, are we still going to talk? You didn't respond to my email.
Oh, yes, I'd love to, Hoshin.
Okay, so as soon as I get off here, give me 5 minutes or so, and I'll send you a Zoom link. Okay.
Fantastic. Thank you.
All right, thanks, guys. I really appreciate you listening and your feedback and comments. And please keep those comments coming because, as you can tell, I find this a very interesting subject. And Joseph, thanks for that link. I add something to my vocabulary, Markov blankets, which I didn't know about before. I'm going to have to read that and understand it. All right. You know what I tell my students, just last comment, now I tell my students in class that I'm not teaching you anything other than a language. When you come to class, all I'm giving you is some concepts and some grammatical rules for how to combine them. When you look at it that way, the world becomes very interesting. Everything's just a language. Yeah. All right. Bye, guys.
Thank you. Bye-bye.
Bye. Thanks, Lila.